want to do two things in the section 9.3 on the integral test and P-series. So one, I want to prove the integral test, and then secondly, I want to mention the little section project talking about the harmonic series in this section. So the integral test, again, it says in your notes, assume f is positive, continuous, and decreasing for x greater than or equal to 1. So for example, your function could do something like this. Okay, so for x greater than 1, we're decreasing, positive, and continuous. And we're going to assume that the sequence an matches the values of fn. So a sub 1 is f of 1. So a sub 1 is here. A sub 2 is f of 2, which is here. A sub 3 is f of 3, etc. You keep going. Okay, so the y values of your sequence, the values of your sequence are the y values of the function. Well, if all these hypotheses are true, then the series sum of an and the improper integral from 1 to infinity of f of x, either both converge or both diverge. So this is nice. We already know how to handle improper integrals. We've already done that. And so if you want to know what the series does, you just evaluate the improper integral. So once again, in math, we're relating something new to something we've already done. Okay, so let's try to see why this is true. So I'm going to consider this picture that I've already drawn here. So I'm chopping up the x-axis along the integers 1, 2, 3. So notice in this situation, delta x is 1, right? Delta x is 1, 1, 1, 1, 1 forever. Okay. Let's use right endpoints. So remember in Calc 1 when we're doing areas under curves, I'm only going from 1 to infinity here because it says from 1 to infinity. Keep in mind, if the sequence was starting with a2, then you would change the integral test by starting at 2 here, okay? So if your sequence is a1, a2, a3, you start with 1. If it starts at a3, a4, a5, you'd start with 3 here. Okay, so I want to use what I say, right endpoints. Okay, so here's the first interval. I take the right endpoint, go up until I hit the graph, and make that the height of the rectangle. Second interval, go to the right endpoint, go up till I hit the graph, make that the height, etc. I go to this interval, go to the right endpoint, go up until I hit the graph, make that the height. Okay? Now, what are the areas of the rectangles I've done here? So the area of the inscribed rectangles, they're sitting underneath my curve. Well, how to do areas of rectangles? It's base times height, plus base times height, plus base times height. Now, I'm only doing the rectangles up to here. I'm not going forever, but I'm just going from here to here. Well, notice the base is delta x. The base is every one is 1, so it's base times height plus base times height. So it's 1 times height plus 1 times height plus 1 times height. But what's the height of the first rectangle? It's f of 2. And the height of the second rectangle is f of 3. And the height of the last rectangle here is f of n. Again, that's the area, because the base is 1, the height's f of 2. That's the area of the first rectangle. Base is 1, height is f of 3. That's the area of the second rectangle, all the way down to the end. All the way down to the end. Okay? And of course, this is the same thing as the sum I equals 2 to n of f of I, if we want to write it in the sigma notation. Okay, let's do the same thing. Let me draw the picture again over here. 1, 2, 3. Okay, but this time I want to use left endpoints. Okay, if I use left endpoints, the first interval here, the left endpoint's 1, make that the height of the rectangle. The second interval, the left endpoint is 2, make that the height of the rectangle, etc. The last rectangle, left endpoint's n minus 1, make that the height of the rectangle. So if we do the same argument here, the area of the circumscribed rectangles, so that means they're outside, is, again, the base is 1, so base times height of the first rectangle is f of 1. So f of 1 is the area of the first rectangle, plus base is 1 times the height of the second rectangle is f of 2, so that's the area of the second rectangle. And you keep going, and we get to the last rectangle here. The base is 1, the height is f of n minus 1. Okay, so we have the area of the inscribed rectangles, the area of the circumscribed rectangles. And again, in summation notation, this is the sum I equals 1 to n minus 1 of f of I. Okay, so that's where we are. Okay, so now how does this relate to the definite integral? So this right here, this f of 2 plus f of 3 plus dot 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 plus f of n. Notice that's the area of the inscribed rectangles. Notice that area is going to be less than the area under the curve from 1 to n, isn't it? Right? Because the rectangles are all sitting underneath the curve. So this is the area of the inscribed rectangles. That's less than or equal to the integral from 1 to n of f of x dx, isn't it? Right? Because the integral from 1 to n of f of x dx is the area under the curve, which is clearly bigger than the area of the rectangles. Likewise, the area of the circumscribed rectangles, every single one of these rectangles includes, right, the area under the curve. So the area of the circumscribed rectangles is going to be larger than the area under the curve. So this integral is going to be less than what we got here, f of 1 plus f of 2 plus dot dot dot, f of n minus 1. So notice I've trapped the area under the curve from 1 to n between two sums. Right? So that's what we've done. Okay? Now, using our notation, remember Sn, our sequence of partial sums, right? Remember Sn is a1 plus a2 plus dot 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 plus an. But notice here, we're assuming a sub n is f of n. So a of 1 is f of 1, a sub 2 is f of 2, etc. Right, so I'm just replacing the ai's with f of I. We assume that was true, right? F of 1 is the same as a1. F of 2 is the same as a2. So let's rewrite this compound inequality in terms of SNs. Notice here I'm missing f of 1, but notice what I can do here. If I subtract f of 1 from both sides, I get Sn minus f of 1 is f of 2 dot 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 f of n, which is this. Right? So again, Sn is equal to that. Subtract f1 from both sides, I get this. That is equal to that. So notice I have Sn minus f1, that's what that is less than or equal to the integral. Now what is the sum of f1 through fn minus 1? Notice S sub n is adding up f1 to fn. So if you add up from f1 to fn minus 1, this is Sn minus 1. Remember, the subscript is telling you how many terms to add up. So Sn is f1 through fn. Sn minus 1 is f1 to fn minus 1, and that's what this side is. So I've just rewritten this in terms of Sns. That's what we have here. Okay, so that's the work. Right? That's all the work we need. Now we need to actually get to the theorem. This is the setup we need to actually prove the theorem. Okay? So let's assume the integral from 1 to infinity of f of x dx converges to L. Right? So if we assume the improper integral converges, we have to show that the series converges, right? Because the theorem says either both converge or both diverge. So if I assume the improper integral converges to L, I have to show that the series converges. Now again, if the improper integral converges to L, so this integral is L, that doesn't mean that the series converges to L, okay? It could be completely different. Okay, so let me come back to the inequality here. I want to rewrite this. Right, so Sn, we're assuming the definite integral converges to L, the improper integral. So Sn minus f1, well that's less than or equal to the integral from 1 to n of f of x dx. But isn't the integral from 1 to n going to be less than or equal to the integral from 1 to infinity of f of x dx? Right? Because this is the area under the curve from 1 to n. This is the area under the curve from 1 to infinity. So that is clearly going to be bigger than or equal to that. And we just said that that is L. So if you solve for Sn, so add f of 1 to both of those, Sn is less than or equal to f of 1 plus L. But f of 1 is just a constant, L is some constant, so Sn is always less than or equal to f of 1 plus L. Okay, so that's a constant. So you have every element of the sequence of partial sums is less than this number, whatever it is. Okay, notice this sequence Sn is bounded above. It's always less than or equal to this constant. Well, remember, f was positive, constant, and decreasing. So positive is the key here. Isn't Sn always going to be bigger than or equal to 0, right? We assume the function was positive, so the sequence of partials, a1, which is f1, is positive. So s1 is bigger than that, and notice when you add s1 plus s2, you're adding another positive. So notice what I have here is Sn is trapped between f of 1 plus L and 0. In other words, Sn is bounded. So Sn is bounded. So the sequence Sn is bounded between these two numbers. It's bounded above by this and below by this. Now, I hope you also agree, isn't Sn, the sequence, going to be monotonic? Right? Because S1 is A1, S2 is A1 plus A2, etc. Every single one of these A values is positive. So if you have A1 and you add a positive number to it, you're going to get bigger. And when you add 3 to that, S3, you're going to get bigger. So the sequence is actually increasing, which is monotonic. So notice the sequence Sn is bounded, and it's clearly monotonic. And we had a theorem that said if a sequence is bounded and monotonic, the sequence converges. So this tells me that Sn, the sequence, converges. But remember, what was the definition of the sum of the series? Remember, the sum of the series, the sum of An, is the limit as n goes to infinity of the sequence of partial sums. We just said Sn converges, so you're going to get a number answer here, which tells me that the series converges. So if the improper integral converges, that tells me that the series converges. Right? So that's one part of it. And now the other part is, let's assume the integral from 1 to infinity of f of x dx diverges, okay? So again, the theorem says if your improper integral diverges, the series has to diverge. So that's what we have to prove next. Okay? Now, I had up there a second ago, we had Sn minus 1 is bigger than or equal to the integral from 1 to n of f of x dx. Okay. Let's take the limit of both sides as n goes to infinity. Okay. So we proved this a little while ago. So notice that any compound inequality I had to the convergence part, I used one, this was less than or equal to this, and for the divergence, I'm using that as less than or equal to that. So take the limit of both sides. Well, what is the limit of this? As n goes to infinity, the integral from 1 to n, by definition, that's that improper integral. Right? That's the improper integral we were trying to show. We assume this improper integral diverges. So this goes to infinity. Well, or minus, it can't go to minus infinity because f of x is positive. So this is blowing up to infinity, and we just have, right, the limit of the sequence of partial sums has to be bigger than that. If this is blowing up, that means that blows up. And remember, the limit of the sequence of partial sums, I know the subscript isn't n, but the limit of Sn minus 1 is the same as the limit of Sn. So if this is blowing up and this is bigger, that will blow up, which means the series diverges. So if the improper integral diverges, the series diverges, and we've now proved the integral test. So it's a very nice, clever proof using areas under curves. Okay, now let's talk about the section project. This is on page 615. And this is just kind of interesting, I think. So we're talking about the harmonic series here. So the sum n equals 1 to infinity of 1 over n. So that's 1 plus a half plus a third plus dot dot dot. And if you started at, instead of starting at 1, if I started at 2 and said a half plus a third, I still would refer to it as the harmonic series. Even if it doesn't start at 1, I still call it harmonic. It's harmonic-like, so I just say it's a harmonic series anyway. Okay, so we learned in class, right, because this is a p series, this is n to the first and p is 1, we know that this series diverges. Okay, so we did that in class. So the series diverges, and so we want to talk about, first of all, they mentioned in part A, let me write more terms out so I can explain part A. Plus a fourth, plus a fifth, plus a sixth, plus a seventh, plus 1/8, and then plus a ninth to the 16th, and then a 17th, all the way out to plus 1 over 32. Okay. So they mentioned Bernoulli explained a way to show that this series diverges, right? By looking at, if you take a third plus a fourth plus a fourth is bigger than a half. You can check that. And if you go a fifth to an eighth, that is bigger than a half. And if you go 1/9 all the way to 1/16 and add those terms up, that's bigger than a half. And 1 over 17 to 132, that's bigger than a half. Notice what we're doing is the denominator is a power of 2. 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth. So the next one would be 1 over 33 all the way up to 1 over 64. So notice you have 1 plus a half, plus a number bigger than 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 a half, etc. If you keep adding terms that are bigger than a half forever, it's not going to converge, right? It's going to blow up. So that's one argument. So that's part A. Okay, so for part B, B says to use the proof of the integral test to show this certain inequality. Okay, so remember what we did above. We got the following. The sum I equals 2 to n of f of I was less than or equal to the integral from 1 to n of f of x dx. Okay, so we proved that a little while ago, up above. Yeah, right. Okay, so in particular here, let's let f of x be 1 over x. Remember, we proved this for any function that was positive and decreasing and continuous for x at least 1. This function is positive, continuous, and decreasing for x greater than or equal to 1. So we can apply that right here, and we can apply this on this side too. So notice f is f of x, so if you plug in 2, that's a half plus a third plus a fourth plus dot 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 plus 1 over n. So I'm using f of x as 1 over x, so 1 over 2, 1 over 3, 1 over 4, all the way to 1 over n. And if f of x is 1 over x here, right, what's the integral from 1 to n of 1 over x dx? Well, the integral, that's natural log absolute value of x from 1 to n. And again, 1 and n are positive here, so that's natural log of n minus natural log of 1. The natural log of 1 is 0, so you get natural log of n. Okay? So notice if we add 1 to both sides of this inequality we just got, we get 1 plus a half plus dot 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 plus 1 over n is less than or equal to 1 plus natural log of n. And notice that is half of the inequality we're supposed to show in part B. If they have a compound inequality, so we have that is less than or equal to that, that's one part. Now they also have something over here, so that's what we need to address now. So if we do the same thing, okay, so we got that. Let me write it up here. Okay, so we just showed that, and that was using stuff we did before. Let me go back to our little basic picture we had before. Again, now I'm using 1 over x. Okay, this time I'm going from n to n plus 1. Now I want to use left endpoint, so if I use left endpoints and draw my rectangles again, notice I'm getting, they're circumscribed rectangles. Okay. So the integral, right? The integral from 1 to m plus 1 of 1 over x dx, this is y is 1 over x. So I'm integrating from 1 to n plus 1. Notice that's the area under the curve, right? That's the area under the curve. That is clearly going to be less than or equal to the area of the rectangles. Okay, so the area under the curve, the way, this continues, right, et cetera, et cetera. Right? The area under the curve is going to be less than the area of the rectangles because the rectangles are sticking all above the curve. Well, what's the area of the rectangles? Well, again, the base is 1, the height is f of 1. So base times height is f of 1. The base is 1, the height is f of 2, it's f of 2, etc. Now notice the last rectangle, the base is 1, the height is f of n. But what it's f of 1, f of 2, etc., right? Remember, we're doing 1 over x, so that's 1 over 1, 1 over half, etc. And we know we can integrate this. Again, this is natural log absolute value of x. Again, those are positive, I don't need absolute value. From 1 to m plus 1. So this is natural log of m plus 1 minus natural log of 1 is 0. So that's what we have proven here. So notice this is the same expression as what I have here. So on the other side, I have natural log of m plus 1. Okay? So what I did before gave me this one. What I did here gave me this one. Okay? So that's what we were supposed to do in part B. Now I'm skipping to part D. It says use the inequality above with n equals 1,000,000. Because it says show the sum of the first 1,000,000 terms of the harmonic series is less than 15, right? So if I plug n as 1,000,000 in here, so I'm on part D here, this is natural log of 1,000,001 is less than 1 plus a half plus dot 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 plus 1 over 1,000,000 is less than 1 plus natural log of 1,000,000. Right? Let n be 1,000,000, n be 1,000,000, n be 1,000,000. Well, if you just punch this in the calculator, what's natural log of 1,000,001? I'm getting about 13.8816. So let's just with that. So let's now what's 1 plus natural log of 1,000,000? I'm getting about 14.816. So notice what this is saying. If you add up the first 1,000,000 terms of the harmonic series, you're somewhere between 13 and 8 and 14.8. So remember, the harmonic series diverges. So if you keep adding and adding and adding, it's going to blow up, go to infinity. But notice if you add up the first 1,000,000 terms, you're only around 14. So this harmonic series, it grows, it goes to infinity, but it grows very slowly. I mean, you add 1,000,000 terms, you're barely, you're in the teens. Okay, now let's go back to part C. Part C says use part B to determine how many terms you would need so that the sum of 1 to big M is bigger than 50. Okay, so here they want us to do, right, the sum I equals 1 to M of 1 over I, we want that to be bigger than 50. So we just saw if you added up 1,000,000 terms of this, you're between 14 and, 13 and 14 or whatever it was, or 14 and 15. 13.8 and 14.8. So they say, how many terms would you have to add up to be more than 50? Wow. Okay, so if you use the inequality above, right here, so let n be m, so natural log of m plus 1, which is less than 1 plus 1 half plus dot 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 plus 1 over m. All right, so we know that's true. And we want to know how many terms, 1, 2, 3 to m terms, how many terms do we need for this to be bigger than 50? So I want natural log of m plus 1 to be 50. Well, right, let's just set natural log of m plus 1 equals 50. And as a log equation, we just want to solve for m. That tells us how many terms we have to have. Well, to solve a log equation, you take the exponential. So if I take e to the both sides power, e to the natural log of m plus 1 is m plus 1. And so m is e to the 50 minus 1. And if you punch that in, this is approximately 5.1847 times 10 to the 21st power. That's tremendous. Think about if you have to add up this many terms for how many terms it is. So this many terms you have to add up in the harmonic series to reach 50, to be bigger than 50. That's a lot of terms. And notice you're only at 50. So again, the harmonic series diverges, but it diverges slowly. I mean, you add, you add this amount of terms and you're only at 50. Okay, so that answers all the questions in the project.